Hello, everyone. So my name's Matthew Cliff. I'm from the University of Nottingham, and I'm very pleased to welcome you to the first scientific session of IWAM. So we've got three fantastic talks for you over the next hour and a bit, and yeah, it's going to be. I'm really excited to hear about the science that we're going to hear. It's all fantastic stuff. So. It's going to be great. And our first speaker is Professor Xiaodong Zhu from the University of Stockholm, where she's Professor of Structural Chemistry and distinguished Professor of the Swedish Research Council as well. So there's so many prizes for all the different speakers. I'm not going to list them, so they would just take too long. But she's going to be telling us today about the power of automated electron diffraction for the materials discovery. So. Come to the stage, Xiaodong. It's going to be fantastic.
Thank you very much. Thank you. I would like first to thank Tony for inviting me to give this to this fantastic place and a fantastic workshop. And so actually, you were the inspiring person for me when I entered the field of porous materials. I read your review article in 1999 on open framework inorganic materials. So that's how I started my career as for developing new porous materials. And so today my talk I want to give you some a new technique, hopefully everybody can use for studying your new materials that you developed using automated and high-throughput electron diffraction techniques. And I have been working in the field of porous materials since 2000, and developing new porous materials starting from open framework germinates and the zeolites and the microorganic frameworks. And it has been a very nice journey. So what technique I mainly used was single crystal X-ray diffraction in order to know all these beautiful structures. But however, it's not always easier to get these materials. So if you want to use single crystal X-ray diffraction, and you have to use synthesized large crystals. And a lot of structures have been analyzed, determined using single crystal X-ray diffraction. In the Cambridge structure database, there are more than 1.2 million different structures. And but if you don't have large enough crystals, you can also use an X-ray powder diffraction. And in this case, you need to have either pure phases, and in the case of single crystals, you need to have larger crystals. But very often, if you have powder, you sometimes don't get a very beautiful powder pattern. So very broad peaks, very few peaks, that's the case. It's difficult to get the structure. And sometimes you get too many peaks, a lot of peaks. So these are the cases that you really can't do very much about. And what to do till you go back to the lab and trying to grow large crystals, or you're trying to make pure samples. But this is very time-consuming, and you really don't know if you have found any new materials, or you're just a mixture of many different materials. So this generally takes a lot of time, and sometimes you give up and you put your sample, throw away them. So, but if you use electron microscopy, and these small multiple phases samples and very broad peaks, and they can be studied using electron microscopy. And since the last 35 years, when I started my PhD at Stockholm University, I have been working with developing electron crystallographic method for just studying these types of materials that cannot be studied using X-ray diffraction. And we studied actually from images. When you have images, you get both the structure factor, amplitude, and phase information. You can directly get the structure. And this has been quite useful for studying materials, specifically if you have material with very small defects. So for example, in this case, so you just with a very small area, and you can obtain the amplitude phases from this image, and combine them to get the 3D structure. And however, this method is very time-consuming. You need a very experienced people to start, and also it doesn't work if you have very beam-sensitive materials. And so this generally takes years to solve a structure. And of course, for the chemists, for the material scientists, you produce a lot of materials already every day. And it really doesn't work. So in the last 10 years, we have been working with developing techniques for based on electron diffraction. I will tell you, using electron diffraction and the materials analysis can be very fast, and it can be very used for most everybody. So I will, in my talk, I will mainly talk about the 3D electron diffraction and also zero electron diffraction. And the electron diffraction has not really been very used. Even the electron diffraction was discovered almost in the same time as X-ray diffraction. The main reason is that, like what you see here in the textbook, and the main reason is that they think that electron diffraction intensities are not reliable and cannot be used for structural analysis. This is in the textbook. And the electron diffraction really is very minor part of the whole solid state chemistry. So comparing with X-rays, neutrons, and the electron microscopy. And so this is basically everybody thinks that electron diffraction is not, intensities are not really useful. And another thing is that electron diffraction also is not useful for as a routine method for phase identification. It is because that you need expertise. So you really cannot be used like X-ray diffraction. That it's easier to just like a fingerprint to get the structure. And so this is the main reason that why not very many people are working in this field. And as you see here in the diffraction patterns, this is the diffraction pattern exactly from the same crystal, but from different areas of the thickness. So this is the thin area, this is the thicker area. It's getting thicker. You see that it is true that the intensities are completely destroyed. And of course, people think that it's not very useful. Until, but the early days, actually, my group have been trying to use electron microscopy and to study the structure. So this is several examples we really show the electron diffraction actually are useful. You see here, so this is a combination of image with electron diffraction and get this structure. It works. And we also used electron diffraction to refine the structure obtained from the images, like it here, 1996. And it shows that the intensities actually are very useful, so you can refine the structure using the intensity extracted from the electron diffraction patterns. And later, we also shown that it was possible to solve the structure using electron diffraction data and directly, so by direct methods. And this, it works, but this were only from a sample which very small short z-axis. So it's, in one projection, it was possible to get the structure. But in the most cases, it was still difficult. Until 1994, and Roger Vincent and Paul Midgley, they discovered precession electron diffraction. And well, instead of you take diffraction patterns along the zonal-axis, it's you tilt the beam, electron beam. So this was the diffraction pattern you will see here. It's like off the zonal-axis. But if you combine them together, and so this will be precession electron diffraction. And they find out actually comparing with normal electron diffraction without precession, and the intensities are much better, so more kinematical. So this has been important. The dynamical effects are reduced if you take diffraction from off-zone axis. And this gives a hope for the electron crystallography community. And then, because of that, the 3D electron diffraction has been developed by different groups. And the first group was by Otto Korb's group in Germany, and they call it automated electron diffraction tomography. Our group developed it called rotation electron diffraction. So it's just by different techniques with the Korb's group combined with precession technique, and my group is using rotation, so they use electron beam rotated, and in combination with the goniometer tube. And later, Tommy Gauner's group developed, they call it micro-ED. But they are all the same, that you tilt the crystal in an arbitrary orientation and continuously, and then you collect the data. So that is what I've shown here. You see here, the data is collected. The crystal is continuous tilt, and you have a camera very fast. You collect the diffraction patterns at different orientations as a movie. And this data collection, when you collect the data, you can get, you combine this data in the software, and you can get the 3D electron diffraction information. Using these ones, and you can obtain the unit cell parameters directly from the 3D electron diffraction data, and you can determine the space group. You can index the diffraction spots, and finally extract the intensities that can be used for structure determination if you don't know the structure. And so using 3D electron diffraction, it's that directly you can determine, make phase identification. Well, it is difficult when you have mixed samples. You can directly do it by electron diffraction. And if you don't know the structure, you can immediately determine the structure in the same way as X-ray diffraction, using the intensities and using exactly the software developed by X-ray diffraction. I give you just a few examples about the impact what 3D electron diffraction can make in terms of the discovery of new porous materials. And this is a zeolite, actually first reported in 1981 by Mobile, but as you see, the crystals very, very small, and it was difficult to get the structure until almost 30 years later, and we studied these samples. We found out actually it was a very nice structure, so very large unit cell, 45 angstrom. We determined the structure using electron diffraction, and not only that, so based on this structure in connection with the already discovered structure like a polling guide, and we find out that there is a structural relation from that, and we could also predict several new structures related, and also synthesize those structures. So all this series of structures contain 8 membered rings, which is perfect for CO2 separation. And this is what you see here, the different zeolite that can be used for CO2 separation. And now, today, during the last 10 years or more, and 80% of newly discovered zeolite structures are determined by electron crystallography. So it has been made a very large impact in the field of zeolite. And many unknown structures that was already synthesized many years ago and could be now determined using electron diffraction. we have also, in collaboration with Omayagi's group, determined the first single crystal structure of a COF, covalent organic framework. And it's interesting here, the structure actually have different structures at different temperatures, and we could study this, both the structure at low temperature and high temperature. You'll see electron diffraction. And now, today, when you use the continuous rotation data, the data collection is extremely fast. So this is the example of electron diffraction data collected just 70 seconds. And for MOF, and you see the resolution is very high, 0.8 angstrom. And you can obtain the structure directly. So this is the structure obtained from this data. And you can do the reticular chemistry. You use different linker, you get a different structure. All these structures could be directly solved using electron diffraction. When we have this, using electron diffraction, and it's not only the framework atoms can be determined, you can also study the gas molecules. In this case, we could see the solvent molecule here and the water molecule here. So they form a network. So they can be all determined using electron diffraction. In this case, you need a low temperature because to fix the molecules, because the microscope is in vacuum. Now, in our lab, and we do not use any more single crystal X-ray diffraction, even we have that, and most of the materials we synthesized, we do not need to optimize to get the larger crystals. Immediately, we can use electron diffraction to study the materials. So this is a project that working with my former PhD student, Ken Inch. He and his PhD student is using our new linker. It's called the polyphenols, and this linker to make different MOFs structures. And because it's a it's from those linker can be extracted from the natural waste. And so using this with bismuth, he made this SU101, and the structure could be directly solved again by using electron diffraction. And this has it's very stable structure, and it has hydrogen sulfate uptake with very good properties. And another one, SU102, it's when you use zirconium and they get another new MOF structures with this allergic acid, and a very beautiful structure. And the structure was again solved by electron microscopy. You see the crystals are very, very small. And it has a very high resolution image to show that it has a very large hexagon porous structure. And this one is interesting. It can be used for treat the pharmaceutical waste from the pollutant from the wastewater. And it's an anionic framework, so that the cationic pharmaceutical pollutants can be absorbed, as you see here. So it's now not only in that you can use electron diffraction for solve the structure, you can use it also for detect new phases, or specifically electron diffraction is powerful to study multiple phase samples. This is an example in collaboration with Carpet Lead Risk Group in University of Oslo. And as you see here, and you have, we find, they are studying the influence of water on the synthesis of UiO67. And we find out when the water contents decreases and there are some new peaks coming, as you see here. But these peaks are so weak, it's almost impossible to identify what they were. And if you look at the high resolution, the SEM images, you see that you find the typical UIO 67, and you have this plate-like structure, crystals. And using electron diffraction, so you can from this UIO 67, so we could collect the data with 0.9 angstrom resolution data and solve the structure. So this is quite straightforward. And if you use, look at this plate-like crystals, and we find actually this is the MIO 100C, and the structure was predicted, but this was the first time it was determined using electron initially. And not only we can solve the structures, and specifically in this case, as you see here, we can actually using when you have very good data, we can study the motions, the molecular disorders, and in the structure in the same way as single crystal X-ray diffraction. What we look is the what is the anisotropic atomic displacement parameters to see how it behaves. And if you look at the UIO 67 structure, and this is the structure we solved, so we can refine the anisotropically, and you get the ellipsoid, and you find out that if we, this is a comparison with single crystal X-ray diffraction, so we get the structure is very similar, and even the allocation of the linker atoms, and it can be directly determined in the same way as X-ray diffraction. But more interestingly, if you look at the 140C structure, and we find out in this structure there were two linkers, linker 1 and the linker 2, and they have very different anisotropic, what's called the ADPs, displacement parameters. And we find out actually in this case, and the linker 1, and it has, because it has a motion, it is vibrate here, and while in linker 2, because they are pi-pi stacking and they are not, they are more stable. So, so because of the data is so good that it's possible to really see these differences between the structures. And you can also look at the hydrogen. So this is quite important because electrons interact much stronger with hydrogen combined with X-rays. And in this case, the hydrogen position could be determined, which is quite important if you want to study the no-covalent interactions between the different parts of the of the structure between different molecules. So in this case, all different types of interactions or no equivalent could be revealed by looking at the interatomic distances. Through the during the past years, and we have solved a lot of structures, and not only zeolite, MOFs and COFs, we even look at the pharmaceuticals and even proteins. So the electron diffraction structure determination can be now in the similar way as what you find in X-ray diffraction. And it's now many people send me the samples, want me to help them to solve the structure. And I think it's not possible for me to take care of all the samples. So during the last years, we are trying to develop methods, and hopefully we can make it automated and easy to use, and that can be accessible for most of the people. And because you don't need a very fancy microscope, it's a standard microscope will work. And so this is a platform we developed. It's called Instamatic. In this platform, where what we can do is that we do the we call the continuous rotation electron diffraction. We make the screening of the data, crystal screening automatically, and then select a suitable crystal to collect the data. And we hope we will use machine learning in the future to do this. And then we can collect the data assisted by crystal tracking. If you collect data, the crystal may move. And then data processing integrated with the existing software developed by X-ray diffraction, and we also make the online data solution. And also that we are developing the energy-filled electron diffraction, where we hope to be able to see the charge of the crystal. In order to make everything work in a pipeline, so we developed what's called the zero-ED and the zero-red. So this was done actually with a very simple microscope. This is a gel microscope used, very standard, and with a very fast camera. And now it's possible to work also with the FEI's microscope. And so this is the example of the, I would say, zero electron diffraction. What we do is that you define an area you want to collect data from, and this area will be like on the grids. And then on each of this grid square, and the program go there to take images. From the image, we identify where the crystals are, and for each crystal, we collect one data. So it's one crystal, one diffraction pattern. We don't tilt the crystal. In this way, the data collection is very fast, and you can screen several thousand crystals per hour. And with all this data, and you can do the data analysis. In this way, we want to find out if there are good crystal, diffracting crystal, bad diffracting crystal, where we're using the deep convoluted neural network to distinguish different diffraction patterns. And this, we use many diffraction patterns to train this data. Finally, so this is the example. We give a score for each diffraction patterns and to see what you get. Using this one, we will also index the diffraction patterns. So in this way, we can collect the data in a fast way and decide if which crystal correspond to which phases. So for example, in this way, so you see that there are 4 different phases in this crystal. And not only like zero ED can give you very good to the phase identification, you can also use it for structural determination, especially for very beam sensitive materials. For example, this zeolite, when we mentioned before, and if you use just the 3D electron diffraction data, and the resolution was 2.5 angstrom, but if you use zero ED data, you can get to 0.8 angstrom, because you put all electrons into one image. And then you can combine many different images together to solve the structure. So in this case, we used 393 different crystals to get one structure. That also works. And if you have unknown phases, you want to determine the structure, and then we developed zero electron red. That means that you collect the 3D electron diffraction data and from different crystals in the automated way. And in this case, you can do the automated crystal finding. You decide if it's a good crystal, bad crystal, to collect the data. And finally, you collect the data, you convert the data, then you do the structure solution in the automated way. And so I will just give you one example. This is in connection with the high-throughput method zeolite development. And in this case, we are using different framework-forming atoms. In this case, it's aluminum, and silicon, and boron, and germanium. And when you have so many different elements in combination with one structure directing agent, and you can generate many different phases. So you will change the condition. So this is a typical high-throughput synthesis you make. So change different ratios, and you get a lot of samples. And most of the samples can be studied using powder XRD, but this part of the samples here, they are too complex to be studied by X-ray diffraction. So in this case, we used rotation electron diffraction. So I just give you one example here. So this is the most complex one. And the samples, of course, very, very small crystals and complicated diffraction patterns. And we collect data of 340 different crystals in 6 hours automatically. And then after that, we process the data, we make the hierarchical, analyze the data based on the hierarchical clustering analysis. And that is what you see here. You find there are many different phases based on the unit cell parameters. And so 3 major phases and actually 2 minor phases. This one is found it's only 1 time. And they are all zeolite structures. Actually, this structure sample was synthesized already 2018 and 2015. So before zero red was developed, in 2018 we started work with this structure and find out actually there were so many phases, and so different new zeolite structures. And some of the structures, as you see here, you can't really find it easily. And the last 2 ones, they have, in terms of the morphology, they have the same morphology, difficult to find from SEM. And these 2 structures have very similar unit cells, even. So it's very difficult. So you can see that when you just very few peaks are different. And so this is like a summary, so that I have shown you that electron diffraction can be used and will be very useful for developing new materials. Actually, there are many different solutions for you to use, and if you can use just a standard microscope, and you just need to have a holder that can have a longitude and to collect the data, and then you need a camera that can take many diffraction patterns. That's all. And then you can there are different commercial possibilities from the software-based, from some artificial Gatan, and also there are different diffractometers that have been also commercialized for these purposes. And if you want to know more, and we have written an article, a protocol that is step-step how it works to use electron diffraction for structure determination. You can have a look at them, this article. And last thing I want to do is it's not only for using electron diffraction for structure determination, for phase identification. Actually, you can do reactions by using electron diffraction. So this is a liquid cell we are developing in collaboration with Christian Muhav's group in DTU, Denmark. And you can see that we can grow crystals into these nanochannels, as you see here, and collect the electron diffraction data and solve the structure. So this is a new, like with aluminum cluster, glycine clusters, and very nice framework, and that the structure could be solved directly from these nanocells. So there are a lot of potentials for electron diffraction, this is the final slide. So I will want to say that 3D electron diffraction really will give you a lot of important contribution for your work. And so it can determine the structure, different anodes crystals, and you can get different, lot of structural information. You can look at the gas molecules, look at the motions. You can do phase analysis. And it can be applied in wide range of materials, from very hard materials to very soft materials. And this has been made a very big breakthrough. So like in 2018, it has been identified as the breakthrough of the year by science. And what I want to show, want you to think, when you have the technique now, it works with very complicated samples. You probably can think about how you can modify your synthesis and to make it so you don't need to really make new pure samples and larger crystals. You can probably think it out of the box and to design your synthesis so that to get a sample that you can study, to be studied using electron diffraction. So that you will give you a lot of opportunities. With this, I would like to thank my group members and the former ones, the current ones that contributed to all this work, and also to thank the collaborators who gave me a lot of challenging samples. And finally, thank you for your attention.
Thank you very much, Xiaodong. That was fantastic. It's not every day you see science that's literally rewriting textbooks, so that's great. So if you have we've got some time for some questions. If you have a question, there are 2 mics just in the middle of the audience there, and if you want to just go up to them and I'll call on you. So yeah. Oh yeah, from the front, Tony.
Thank you, Xiaodong. That's a wonderful talk. Having worked on sort of characterizing powders for many, many years, this is kind of revolutionary. So 2 questions. One simple. Are you mainly collecting data at low temperatures with these things, like with the MOFs and the COFs and so on?
The answer is no. So we are mainly collecting data at room temperature, but sometimes at low temperature.
So you do it at room temperature first, and then if you have problems, you cool it down.
Yeah. So if you want to look at the gas molecules, probably you need to have it in the low temperature.
Yeah.
So even the COFs, MOFs, most of them are stable at low room temperature.
So the second question, slightly more sophisticated, have you tried to analyze diffuse scattering as well as the Bragg scattering?
Yeah, that's a very good question. I didn't have time to go through it. Actually, we have started quite a number of samples. They do have diffuse scattering. What we do is that we look at the block peaks, first get the average structure, and then we look at the diffuse scattering to find out what are the disorders. So usually you can figure it out. And then if you have a more complicated diffuse scattering, actually one of my colleagues are developing what's called the PDF to extract the 3D data from including the diffuse scattering to study the disorder.
So I was thinking of 3D PDF.
Yes.
Yes, would be fantastic. Okay, thank you very much.
Thank you.
I think we have a question from the audience.
Yes, I can hear you.
So, ma'am, good morning. So my question is, so whenever we rotate the crystal, every time we are having a diffraction pattern. Okay, so how many, is there any minimum limit ki this, this much number of minimum diffraction patterns we need to form a final structure?
They depend on the structure itself. So the minimum data you need. Sometimes, for example, if we have like a limited tilt, like the one I showed you in the cells, and we have limited tilt, so the completeness is about 35%, but we could still obtain the structure. So it's really depends on the structure. And if you have higher symmetry, and you don't need so many large tilt angles.
Okay. So last question. So is it possible to calculate anisotropy in the material with the help of this?
Isotropic?
Anisotropy.
Yes, so if you have high resolution data, you can refine the structure anisotropically. Most of our structure refinement were done anisotropically because we have the data sub-angstrom resolution.
Okay. So till now, is there any limitation compared to XRD? I mean, is there any limitation?
Yes, it's still that we still have a very high R value comparing with X-ray diffraction. That is not necessarily because the structure is incorrect. It's mainly because the intensities are deviate from the kinematical refinement. And you can do dynamical refinement to get even better structure refinement, but it's more complicated. Most of our structures were solved using kinematical refinement.
Okay, thank you so much. Dhanyavad.
Thank you.
And thank you again, Xiaodong. That was a brilliant talk. And if we could all just give another round of applause to Xiaodong.
Thank you.